Hey everybody, in the last class we did the derivative of a product, and today we're going to do the derivative of a quotient. So here's our conjecture. Our conjecture is that the derivative of a quotient is equal to the derivative of the numerator divided by the derivative of the denominator. And after our experience computing the derivative of a product, we're not going to jump to conclusions and assume that the derivative of a quotient is this thing. We need a test case. And so here it is, a simple case, but it ought to shed some light on whether our conjecture is actually true or not. So let's see. If our conjecture is true, then all we have to do is compute the derivative of the numerator and put it over the derivative of the denominator. And we have the derivative of this quotient. Now let's simplify. The derivative of x is just 1. So our answer should be 1 if our conjecture works. Since this is a test case, we need to have another way of computing this derivative that's completely independent of what we did here. So we have the derivative of x divided by x and the derivative of x divided by x, well, let's see. X divided by x is just 1. So we have the derivative of a constant, 1. And the derivative of any constant is what? What's the derivative of a constant? 0? Okay. Now, x divided by x, that's 1, without any doubt. The derivative of 1, since it's a constant, is 0. We know that's correct. This has to be the right answer because we know that each of the 2 steps that we took here are correct. So this is correct. Oh, but look what we got when we did it the other way. We didn't get the same answer. Yep, we're having another oops moment. This is not right. This has to be incorrect because we know for a fact this is the right answer. So somewhere in the process, we made a mistake. So let's see. Did we make the mistake going from here to here? 1 divided by 1 is 1, isn't it? So we didn't make the mistake here. And the derivative of x is 1, isn't it? So we didn't make the mistake going from here to here. There's only one other place where we could have made a mistake, and here it is. We had to have made a mistake going from here to here. Oh my goodness. Well, it's a good thing we had the test case. At least we can lay to rest now how not to compute the derivative of a quotient. And just like I did with products in the last class, I'm going to do the same thing with quotients in this class. So what we learned from the test case is that if we compute the derivative of a quotient, we don't do it by computing the derivative of the numerator and putting it over the derivative of the denominator. It doesn't work. It seems reasonable enough, but it doesn't work. So don't do this. Whatever we do, let's not do this. Let's not compute the derivative of a quotient, f of x over g of x, by computing the derivative of the numerator and putting it over the derivative of the denominator. It doesn't work. It's a reasonable thing to try, but it doesn't work. And now that we've seen that it doesn't work, let's see what does work. Everybody, this is what the derivative of a quotient looks like. And who in a million years would have guessed that it turned out to look like this? It's not at all obvious, is it? We call this thing the quotient rule. This rule tells us correctly how to compute the derivative of a quotient. So this thing that we are looking at right here, this is the quotient rule. And I think I'm going to erase the title quotient rule just for the sake of diagramming what we have up here. This is another one of these things that's best remembered with a little saying with some rhythm and rhyme. So let me diagram this. I'm going to call this thing the top. I'm going to call that thing the bottom. So what have we here? This is the bottom squared. Now let's go up to the top, the first term. This thing, we'll call this the top prime. And this is the bottom verbatim. Here we have the bottom prime. And this thing is the top verbatim. So that's the derivative of a quotient. And let me tell you what I see here in words. Top prime times the bottom minus bottom prime times the top. So top prime times the bottom minus bottom prime times the top, all over the bottom squared. Now we've been working on our product rule. First prime times second plus second prime times first. We've been working on that. And hopefully we've got that fairly well memorized now. Just remember, say it 5 or 10 times a day for 2 or 3 days, and we'll know it forever. To that, we're going to add the quotient rule. Top prime times bottom minus bottom prime times top all over the bottom squared. Top prime times bottom minus bottom prime times the top all over the bottom squared. Top prime times the bottom minus bottom prime times the top all over the bottom squared. Say that 10 times a day for the next 3 days, we'll know it forever. And when I say that 10 times a day for the next 3 days, I'm actually dead serious. I have a big smile on my face, but I'm dead serious. This is an easy thing to remember. If we just do it several times a day for a few days, we'll know it forever. And knowing this and knowing the product rule will take us a long way as far as computing derivatives goes. And remember the ultimate objective, to get an A in Cal 1. And if we're going to take Cal 2 and Cal 3, we want to get an A in Cal 2 and an A in Cal 3. And the way to do that is to make sure we do well in Cal 1. So there's nothing wrong with memorizing these things. As a matter of fact, I never did memorize these things until I became a good student. And then once I became a good student, I grabbed a hold of every advantage I could get just to make sure I'd do as well as I could. And in retrospect, I did exactly the right thing. So if we want to be good students, grab on to every advantage we can get, memorize these things, it'll pay off. Now, I say that it works, but just like with the product rule, I guess we shouldn't just blindly believe it without applying it to a test case. Why don't we apply it to the test case that we did 5 minutes ago? X over X. Let's just see if it works, okay? This is the bottom. This is the top. And let's see, what does my quotient rule tell me? It tells me top prime times the bottom. So I should have top prime here. Top prime times the bottom minus bottom prime times the top. So I have bottom prime here. Top prime times the bottom minus bottom prime times the top all over the bottom squared. So down here, we need to have the bottom squared. Okay. Top prime, the derivative of x is 1, times the bottom minus the bottom prime. The derivative of the bottom is 1 times the top all over the bottom squared. There. Now let's just simplify it. I have x minus x is 0 over x squared, and that's 0. Did we really do it right? Remember, with a test case, we need to be able to verify our result by an independent method. So here's our independent method. Derivative of x divided by x. We know what x divided by x is. It's 1. So we'll rewrite this as the derivative of 1 and how do we do the derivative of 1? 1 is a constant, and the derivative of a constant is 0. That's right. The derivative of a constant is 0. So, did it work? We get 0, we get 0. Hey, this method worked. This method worked. Okay. So in our test case, the quotient rule did work. And what was that? Top prime times the bottom minus bottom prime times the top all over the bottom squared. Yeah, when I finally became a good student and I was taking Calculus 1 for the 3rd time, I walked all over campus saying things like first prime times second plus second prime times first, and top prime times bottom minus bottom prime times the top all over the bottom squared. Yeah, people must have thought I was nuts. But I'll tell you what, I aced Cal 1. Not only did I ace Cal 1, but my instructor pulled me aside at that point and told me that I should consider getting a PhD in mathematics. So not only did I ace Cal 1, but apparently I did it convincingly. I decided to become a good student. I picked up some good habits like walking around campus saying top prime times the bottom minus bottom prime times the top all over the bottom squared. Yeah, people probably thought I'd lost my mind. But I aced Cal 1, and I aced Cal 2, and I aced Cal 3. And just taking advantage of anything that I could grab a hold of, it paid off. It'll pay off for you too. Now, let's put this to some serious tests. Let's do some real derivatives here. Oh, this is a nice example. And it's going to give us a result that we're going to have to memorize. So this is a great example to be working on. And I look at this thing and I say, how on earth am I going to compute the derivative of tangent? I don't know anything about tangents, especially derivatives of tangents. The only trig functions I know anything at all about when it comes to derivatives are sines and cosines. I don't know anything about the derivative of it. So I guess the thing to do is to rewrite this in terms of things that I know more about, like sine and cosine. I know what the derivatives of sines and cosine, what sine and cosine are. So and in doing this, I actually got to do something that I really like. So I might as well write this down because it's one of my favorite words in the English language. Rewrite. All good engineers, they like to rewrite, they like to draw pictures. Good mathematicians like to do that too. Let's see. Can I do this now? I know the derivative of sine of x, and I know the derivative of cosine of x, right? So I think that we can do this. This is the top, and there's the bottom. We can definitely do this now. I just have to remember the quotient rule. Top prime times the bottom minus bottom prime times the top all over the bottom squared. I got it. So top prime times the bottom. Top prime times the bottom the derivative of sine of x is, what's the derivative of sine of x? Cosine of x? The derivative of sine of x is cosine of x, so that's our top prime, times the bottom verbatim. So I have top prime times the bottom minus bottom prime times the top Okay. Bottom prime. The derivative of cosine of x is, careful now, derivative of cosine of x is negative sine, right? Okay. Negative sine x times the top, sine of x, top prime times bottom minus bottom prime times top, all over the bottom squared. Okay. I need the bottom squared here. Cosine x squared. There we go. Now, technically, I can leave it like this. I've computed the derivative. But there's a universally accepted form for the derivative of a tangent. And so what I'm going to do is manipulate this expression algebraically until I get the universally accepted form for the derivative of tangent x. So let's see what we got. On top we have cosine squared x minus a negative sine squared x, so that's plus sine squared x, all over cosine of x squared. And because I have a selfish motive here, I'm not going to write it as cosine of x. I'm not going to write it as cosine squared x. I could, but I have an ulterior motive for leaving the denominator in this form. Now, something looks very familiar to me as far as the numerator goes. Cosine squared x plus sine squared x, or sine squared x plus cosine squared x. That ought to ring a few bells. And if you're thinking sine squared x plus cosine squared x equals 1, you're right. The numerator is just 1. And now, out of selfish motive and nothing else, I'm going to rewrite the numerator as 1 squared so I have numerator squared over denominator squared. But wait a minute. Don't we have a formula that says x? Let's see, what does the formula say? The formula says x over y to the n is equal to x to the n over y to the n. The exponent distributes to both numerator and denominator. Well, it's an equation. And remember, an equation is a two-way street. Not only can we read it from left to right, we can read it from right to left. So if I have x to the n over y to the n, I can write it as x over y to the power of n, which is exactly what I'm going to do here. Okay, I'm going to write that as 1 over cosine of x, whole thing squared. Yep. That was my devious motive in not writing this denominator as cosine squared x. Now let me ask you something. 1 over cosine of x, what is that? I'm sure it's a trig identity. 1 over cosine of x. Isn't that secant of x? I'm pretty sure it is. Secant of x, quantity squared. And now I'm going to take that and just write it in equivalent form. Secant squared x. Let me reiterate, technically I was done when I got to this point. I had computed the quotient. But just for the sake of getting the derivative of tangent in the universally accepted form, which is secant squared x, I did this extra algebraic manipulation. Now, let me not lose what I've just accomplished. Let me write that down. I started out with the derivative of tangent x. I got secant squared x. This is what we just derived. This is the universally accepted form of the derivative of tangent x. Look in any book on calculus, look for the formula for the derivative of tangent x. That's what you're going to see. And it's going to be one of those things, ta-da, that we have to memorize. I'm not a big fan of memorization, but some things just have to be memorized. There are going to be times when our success in mathematics is going to be dependent on our skills at pattern recognition. And if we haven't committed some of the patterns to memory, we're not going to recognize the patterns. So some things just have to be memorized. And this is going to be one of them. Okay, I'm off my soapbox. Let's do another quotient. This is another great example. Derivative of secant x. And maybe we learned a little bit from the last example that we did. In the last example, we computed the derivative of tangent x, and we looked at it dumbfounded and said to ourselves, I don't know anything about tangent of x. I know something about sines and cosines when it comes to derivatives, but I don't know anything about tangent x. And so we reasoned, let's rewrite tangent x in terms of functions that we're more familiar with, sine and cosine. We know the derivatives of sine and cosine. We have a similar situation here. We don't know anything about secant other than what it's equivalent to in terms of sine and cosine. So let's write secant x in terms of those functions that we're more familiar with. We'll write it in terms of sine and cosine. Provided that we've remembered our trig identities well enough to do that, secant x, that's 1 over cosine, isn't it? So that's how we'll rewrite it. 1 over cosine of x. And now we can use the quotient rule. Here's the bottom, and here's the top. And my quotient rule is starting to click. Top prime times the bottom, minus bottom prime times the top, all over the bottom squared. Yep, I'm getting it. So I will diagram this, or make a template out of it. Let's see, I know I'm going to get a quotient, so I'll write my bar there. And I should get top prime times the bottom and then minus the bottom prime times the top all over the bottom squared and I just fill in the blank, or the blanks. Top prime. Well, the top is a constant, 1. So top prime is 0 times the bottom, cosine of x, minus bottom prime, derivative of cosine of x. What's derivative of cosine of x? Negative sign. So negative sine of x is bottom prime times the top, which is 1, all over the bottom squared, cosine of x quantity squared. And technically, this is the derivative. I'm going to work with it algebraically, though, so that I can work this expression into the universally accepted form for the derivative of secant. So I have 0 minus a negative sign, so that's plus sign on top, sine of x on top, all over cosine squared x, or cosine of x quantity squared. And now what I'm going to do, I'm going to break this up into cosine times cosine. Cosine of x times cosine of x and I can rewrite this as 1 over cosine of x times sine of x over cosine of x We've seen this a few times already in this class, haven't we? 1 over cosine of x. What is it? Secant of x. And sine of x over cosine of x, we know that is tangent of x. And that's actually going to be the universally accepted form of the derivative of secant x. We started out computing the derivative of secant of x, and we got secant of x times tangent x. This is the universally accepted form for the derivative of secant of x. This is our result. Now, these are the only two derivatives of the elementary 6 trig functions that we'll do explicitly. We do have to commit the derivatives of all trig functions to memory. We have to do that. This is one of them that we should memorize. Now I'm going to create a table of the 6 elementary trig functions along with their derivatives. And again, I'm putting it up here because we need to memorize the derivatives of the trig functions. The derivatives of the 6 trig functions. We have to memorize them. And I've put them on the board in this arrangement for a reason. I've put cosine of x opposite sine of x. I've put cotangent x opposite of tangent x. I put cosecant x opposite secant x because there's a similarity in the formulas for derivatives of sine of x and cosine of x. There's a similarity in the derivative formulas for tangent x and cotangent x. And there's a familiarity or a similarity in the derivative formulas for secant x and cosecant x. Now, you can memorize them as they are, which is a good thing. You can use this trick that I'm about to tell you. And without explanation, I am going to say that the co-function of sine of x is cosine of x. And the co-function of tangent x is cotangent x, and the co-function of secant x is cosecant x. Why do I call them co-functions? It's not worth the lengthy explanation. But just know that cosine of x is the co-function of sine of x, and cotangent x is the co-function of tangent x, and cosecant of x is the co-function of secant x. And know this too. Functions and their co-functions come in pairs in the sense that cosine is the co-function of sine of x, but it's also true that sine of x is the co-function of cosine of x. And cotangent x is the co-function of tangent x, and tangent x is the co-function of cotangent x. And cosecant x is the co-function of secant x, and secant x is the co-function of cosecant x. So they come in pairs. They come in co-function pairs, sine and cosine, tangent and cotangent, secant and cosecant. Now here's a pattern that will make things a bit easier to remember. If we know the derivative formula for one function, it's easy to come up with the derivative formula for its co-function. For example, if we know the derivative of sine of x, it's easy to produce the derivative formula for its co-function, cosine of x. And we do two things. We take every function in the original formula and replace it with its co-function. So I replace sine of x with its co-function, cosine of x. I replace cosine of x with its co-function, sine of x. That's the first step. Take each function in the original formula and replace it with its co-function. Replace sine of x with cosine of x. Replace cosine of x with sine of x. That's the first step. The second step is to change the sign out front. If we have a plus out here, we make it a negative. Let's try it with this one. Let's say that we know the derivative formula for tangent x. To get the derivative formula for its co-function, we just take the functions in the original expression, tangent and secant squared, and replace them with their co-functions. Replace tangent with cotangent. Replace secant squared with cosecant squared. So we replaced the functions in this formula with their co-functions over here. That was the first step. The second step, we look at the sign out front and change it. So if it's a positive sign out here, we put a negative sign here. Beautiful. Now, just for the sake of illustration, let's go from here to here. Let's say that we know the derivative formula for cosecant x. To get the derivative formula for its co-function, secant x, we do two things. We take each of the functions in the original expression and replace them with their co-functions. So cosecant, we replace with its co-function secant, and cotangent we replace with its co-function tangent. So we replaced each of these functions with their co-functions. Second step, we look at the sign out front and change it. The sign in front is negative, we change it to positive. Now that's a rule that will help us remember the trigonometric derivatives, and it's a rule or a pattern that will help us keep these things memorized. I may go for 6 or 8 months without teaching calculus, and I'll say, wait a minute now, what is the derivative of cotangent? Oh yeah, derivative of tangent x is secant squared. So just replace tangent and secant squared with their cofunctions. Derivative of cotangent, cosecant squared, and then just change the sign out front. Negative cosecant squared. It's a good memory aid for me, especially when I've gone about 6, 8 months and I haven't taught calculus. And I go, wait a minute, derivative of cotangent, wait a minute, derivative of tangent is secant squared. So derivative of its cofunction, cotangent, will be cosecant squared, and we change the sign out front. It's a good memory aid. Let me say something else also about remembering things. Some of us have had calculus before, and we may have learned some other way of remembering the quotient rule. Something like low d high, high d low, and so forth. If we already have a memory device that works and we've remembered it correctly, you don't have to use mine. If you already have correctly memorized one of these mnemonic devices, go ahead with what you already know. So if you want to do low d high minus high d low and so forth, that's fine with me. Now, what should we do? Maybe one more exercise. I think so. Another quotient rule example. Excellent, excellent, excellent. We got to compute the derivative of this piece of junk here. So, I'm going to lay everything out. Here's the bottom. Here's the top. And I've been doing my quotient rule. I've been walking around saying it. Top prime times the bottom minus bottom prime times the top, all over the bottom squared. I got it. So I'm going to write that down first. So I have top prime times the bottom minus the bottom prime times the top. Let's see, did I do it right? Top prime times the bottom minus bottom prime times the top. Looks good. All over the bottom squared. Looking good. Okay, top prime, we just have to compute the derivative of this piece of junk. 4 times 3 is 12. Subtract 1 is 3, so we have 12x cubed. 6x squared derivative, bring the exponent down front. 2 times 6 is 12. Subtract 1 from the exponent, so that's x to the first. And you know what? I better write smaller. 12x cubed plus 12x. Okay. There's my top prime times the bottom. 3x cubed minus 7x squared plus 5x. There's my bottom. Okay. Now, Bottom prime, derivative of the bottom. Bring the exponent down front. 3 times 3 is 9. Subtract 1 from the exponent is 2, so 9x squared. Bring the exponent down front. 2 times negative 7 is negative 14. Subtract 1 from the exponent is 1. So minus 14x. Derivative of 5x is just the constant 5. See, 9x squared minus 14x plus 5, that looks good. That's the bottom prime. Times the top verbatim, 3x to the 4th plus 6x squared plus 2 all over the bottom squared. 3x cubed minus 7x squared plus 5x. Okay. There's our derivative. And if I'm doing something like this on a test, you know what? I'm going to leave it like this. I'm not going to give a second thought to simplifying it. If somebody put a gun to my head and said, simplify this or else, there's a 50-50 chance I'd simplify it. And maybe not. Maybe I just look at this thing and say, go ahead and shoot me. I'm not going to simplify it. But on a test, leave it like this. Now, if we're doing a homework exercise in our text like this, simplify the result just enough to make sure that our result is equivalent to what they have for an answer in the back of the text. So if we're doing homework exercises from the text, we do want to make sure that we get our answer in the form that they have for their answer, just to make sure that we did it correctly. And this concludes quotient and product rules. I'll be giving you some homework exercises from the text.